Here is a database question that sounds trivial. Can a customer place more than one order? Yes, obviously. Can an order belong to more than one customer? No. An order belongs to one customer. That's what an order is. Now here is the question that matters. Does your database know that? Most databases don't. They store customers in one table and orders in another, and accept any combination of relationships between them, including the ones that make no sense. Unless someone explicitly told the database which combinations are valid and which are impossible, the database will happily store an order that belongs to 3 customers, or a customer linked to an order that belongs to someone else entirely. It won't throw an error. It won't warn you. It will just store it. And that impossible combination will sit in your data, looking like any other row until something downstream tries to use it and produces a result nobody can explain. That's the cardinality problem. And it is hiding in almost every relational database that wasn't designed with explicit relationship rules. Cardinality is the word databases use to describe how many of one thing can relate to how many of another. One customer, many orders. One order, one invoice. Many students, many courses. A student can take many courses, and a course can have many students. Each of these describes a different cardinality. One to many. One to one, many to many. These aren't just design concepts, they are business rules. Rules about what your data is allowed to mean. And like all business rules, they need enforcement, not documentation, not convention. Enforcement. Let me show you what missing cardinality enforcement costs. In 2020, a subscription software company ran a billing cycle that produced invoices for the month. The billing system joined the customers table with the subscriptions table to calculate what each customer owed. The join returned unexpected results for a small subset of customers. Some customers appeared multiple times. The billing system summed their charges for each appearance. Those customers were billed 2 or 3 times their correct amount. The investigation found the cause. The subscriptions table had a customer ID column, but no constraint enforcing that each subscription belonged to exactly one customer. Over 18 months of data migrations, integration updates, and manual fixes, a small number of subscription records had been assigned to multiple customer IDs, a many-to-many relationship in a column designed for one-to-many. The database had accepted every one of those assignments without complaint. The relationship that was supposed to be one customer per subscription had silently become something else in a handful of rows. Not because anyone intended it, because nothing prevented it. 47 customers were overbilled, some by double, some by triple. The refunds went out. The trust damage was harder to repair. Here is how cardinality constraints actually work in a relational database. The primary mechanism is the foreign key. A foreign key is a column in one table that references the primary key of another table. Every value in the foreign key column must exist as a primary key value in the reference table. In plain terms, every order must reference a customer that actually exists. You cannot create an order for customer ID 9999 if customer 9999 is not in the database. The foreign key enforces that the relationship points to something real, but a foreign key alone only enforces existence. It doesn't enforce cardinality. To enforce one-to-many, you combine the foreign key with a uniqueness rule. One customer, many orders. The orders table has a customer ID foreign key. Many orders can share the same customer ID. One customer can appear across many order rows. That's one-to-many. The foreign key enforces it correctly by default. One order, one invoice. The invoices table has an order ID foreign key. Add a unique constraint to that column. Now no 2 invoices can share the same order ID. One order maps to at most one invoice. That's one-to-one. The unique constraint enforces it. Many students, many courses. Neither table references the other directly. Instead, a third table, an association table, holds pairs of student ID and course ID. Each pair represents one enrollment. The combination of both IDs is the primary key, so the same student cannot be enrolled in the same course twice. That's many-to-many. The association table enforces it. 3 patterns, each enforced differently, each requiring an explicit design decision. None enforced automatically just because the relationship seems obvious. This is the part developers most often get wrong. The relationship is obvious in the design. Everyone on the team knows one order belongs to one customer. It's in the requirements. It's in the ERD. It's in the code comments. But obvious understanding is not database enforcement. The database doesn't read the ERD. It doesn't know that one order belonging to multiple customers is nonsensical. It knows what the table definition tells it. And if the table definition doesn't specify the cardinality rule, the database applies no rule. Every migration script that runs directly against the database is free to create any combination it wants. Every integration that writes without going through the application layer can create any combination it wants. Every developer who manually fixes a data problem under pressure can accidentally create any combination they want. Without the constraint, the only thing preventing impossible relationships is every person who ever writes to the database correctly understanding and respecting a rule that exists only in their head. That is not a system, that is hope. There is one more cardinality rule that most teams never think to enforce: the minimum cardinality. Maximum cardinality says, at most how many? One order, at most one customer, enforced by foreign key and unique. Minimum cardinality says, at least how many? Can an order exist with 0 customers, with no customer ID at all? The answer is almost certainly no. An order without a customer is not a valid order. This is enforced by NOT NULL on the foreign key column. An order's customer ID must be NOT NULL, meaning every order must reference a customer. The minimum is 1, you cannot have 0. Without NOT NULL on the foreign key, orphaned records can exist. Orders with no customer, invoices with no order, subscriptions attached to nothing. Each one a data anomaly that queries will handle inconsistently, that reports will count or not count depending on their join type, and that nobody will notice until a billing cycle produces results that don't match the number of customers in the system. When you design a relationship between 2 tables, ask 3 questions before you write the first foreign key. What is the maximum number of times one side can appear? 1 customer per order, or many? 1 invoice per order, or many? The answer determines whether you need a unique constraint. What is the minimum number of times one side must appear? Can an order exist without a customer? Can an invoice exist without an order? The answer determines whether the foreign key must be NOT NULL. What prevents an impossible combination from being inserted? Not what your application code does, what the table definition does. If the answer is nothing, the constraint is missing. 1 customer, many orders. 1 order, 1 invoice. Many students, many courses. These feel like facts about your data. They are actually rules about your data. Facts exist whether or not you enforce them. Rules only hold if something enforces them. Your database will store an order assigned to 3 customers with exactly the same indifference as an order assigned to 1. It cannot tell the difference. You have to tell it. And until you do, every relationship your system depends on is held in place not by a constraint, but by the shared assumption that nobody will ever write a value that breaks a rule that was never written down.